Yes, yes, I can hear you. Sure, sure.
Okay, good evening. We'll start with today's section on welcome to this TA session on computational fluid dynamics offered in NPTEL by Professor Srinivas Jayanti and Sankar H. I'll be your teaching assistant for today from 6 o'clock to 8 o'clock on Mondays. And we are looking at week 8 lectures. And through this session, we'll cover the graded assignments, ungraded assignments, and certain questions, example problems. And if other questions, if anyone still has any doubt.
Your health is better now?
Yeah. Thank you for
Okay,
asking. It's much better. Thanks.
okay.
Okay, let's get started with the graded assignments of previous week. Week number 8, which deals with flows related to incompressibility. And incompressibility generally states that the Mach number is much less than 1, or the flow, it's a property of the flow rather than of the fluid that we are discussing about. So let's first look at this question. Which of the following statements is or are correct about incompressible flows? The first statement is most liquid flows are incompressible. Second statement, flow of air can be incompressible if the flow is sufficiently high. Now, all these questions, one thing is to know that we are talking about incompressible flows, not incompressible fluid, which means that the flow velocity is what determines whether the uh, flow is incompressible or not. So the first question is most liquid flows are incompressible. That statement is generally true as we don't deal with high velocity of liquids will result in a, that's mainly because we result in a high Reynolds number, which automatically goes to a turbulence zone. And generally fluid mechanics and computational fluid dynamics involve the use of low Reynolds number and laminar flows. And and we can see that liquids have generally a considerably high density as compared to vapor phase or gas phase. Therefore, gas can accommodate high velocity as compared to liquid. So most liquid flows are generally incompressible unless otherwise stated. Now, the second point here is flow of air can be incompressible if the flow is sufficiently high. And if velocity is very high, uh, let's say if velocity is very high, then that means that the Mach number, which is defined as the velocity to the speed of sound in the medium, will be much greater than, let's say, our desired value. And this means that a high Mach number means that we'll be dealing with a compressible flow, as we have seen in our last week lectures. Therefore, option 2 is wrong. We cannot say that the flow of air is incompressible if the flow speed is sufficiently high. It is compressible if the speed is high. And all these compressibilities are based just on the velocity of the flow uh, in that particular medium. Okay, moving on to second question. Which of the following is or are the among the difficulties encountered in the solution of incompressible flows? First one, coupled equation. Second one, nonlinearity of governing equation. Third one is determination of pressure. So again, let me just, yeah, there we go. So let me just write down what all we need to solve while we are solving incompressible flow problems. So any fluid mechanics problem will have, we need to have conservation of mass, which is also known as the uh, continuity equation, which is given by del dot u equal to 0 for incompressible flows. And second one is the Navier-Stokes equation, which is the conservation of momentum. So generally, a fluid flow problem that does not deal with changes in temperature has to we have to solve mainly these two equations, not just two equations. This one has three components to it. So basically, we are solving four equations, and when we solve the Navier-Stokes equation, what we are solving is dou u by dou t plus del dot uu is equal to minus 1 by rho times del p plus mu into del square u. So first thing we need to identify is, if we take a component balance over here in the x and y direction, we will be getting a coupled equation in terms of u, where let me write one of the x momentum equations. We can write this as dou u by dou t plus um, dou by dou x of u square plus dou by dou y of uv is equal to minus 1 by rho dou p by dou x plus mu dou square u by dou x square plus dou square u by dou y square. Let me assume that this is just in 2D. So I'm neglecting the z for now, for simplicity. So we can see that these equations I have written down here for the momentum balance equations are in fact coupled over here and nonlinear over here. So therefore we have to incorporate the coupled nature and the nonlinearity of the governing equations while solving for incompressible flows. Now the next thing we have to identify is, how do we find the pressure? We generally, when it's a compressible flow, we solve for we put the couple the density along with the velocity, and then find an equation for and find the density variation in the domain that's given, and equate it using find the pressure using an equation of state, a relevant equation of state for the problem that we are dealing with. But in these cases, in these liquid problems or incompressible flow problems, there is no density variation along the domain we are talking about. So how do we find the pressure field right now? So we find the pressure field by simultaneously solving these equations. Therefore, we do face that problem while solving for incompressible flows. So the correct answer here in this question, which among the following are the difficulties encountered in the solution of incompressible flows? We have to consider the coupled nature of the equation. We have to consider the nonlinearity of the governing equation, and pressure has to be found out while solving these equations, while solving this equation simultaneously. Alright, moving on to the next question. Consider the steady incompressible flow through the contraction section of a circular pipe, so shown in figure. Okay, this is not 7.1, this is 8.1. For this flow, which of the following can be neglected? First one, pressure variation in the flow direction. Second one, density variation in the flow direction. Anyone from the audience would like to answer? It's a very straightforward question.
Density.
Yeah. We are only worried about we are only neglecting the density variation in the flow direction, as it is given that it's an incompressible flow. So therefore we don't have to worry about the density variation, but we do have to find out the pressure field, because this would be the source of flow. Moving on to question number 4. Consider the steady compressible flow. Sorry, this again would be incompressible. I must have copied it wrong here, but steady incompressible flow through the contraction section of circular. Just make this now. Yeah, circular section of a contraction section of a circular pipe shown in figure 8.1. If the flow is unsteady, axisymmetric and viscous, how many partial differential equations need to be solved to get the flow field? Anyone from the audience would like to answer this one as well?
Uh, 3.
Yeah, that is correct. So while we are actually solving for it, we are solving, as I have shown before, we are solving continuity equation, and one continuity equation, and we will have to solve uh, the Navier-Stokes equation. And Navier-Stokes equation will have x component and y component. Since it is directly given that the flow is axis symmetric, we can either solve for xy, or we can also solve for r and z, since considering this to be r and this to be z. And since it's an axis symmetric, we don't have to worry about the theta variation at all in this problem. So we'll have to solve totally 1, 2, 3 equations, and we will be finding out the u and v velocities, or ur and uz velocities, and the pressure field. Okay, let's move on to question number 5. Again, this is 8.1. Must be a mistake, too many mistakes here. For the, again, this is again incompressible flow. For the incompressible flow case shown in figure 8.1, which of the following statements is true about the stream function vorticity method? Option 1, it cannot be used because the flow is laminar. It cannot be used because the flow is three-dimensional. It cannot be used for Cartesian coordinate system. We'll go through this one by one. Can we use the uh, stream function vorticity method while we are in a turbulent regime? Anyone from the audience would like to answer?
I think not. I think it
We
requires laminar, right? No?
Yeah, we can use it even if it is turbulent, but uh, since it's given, what do you say, we can use it if it's turbulent, while we have to write in terms of the deviational velocities, everything, the equation. And 1 second, if we write the equation of Navier-Stokes and continuity in u dash and v dash, which are basically the deviation velocities, we can actually use them. But in this question, we can use the flow if it is in laminar flow, since it's also given that it is an incompressible flow. We could assume the laminar flow, and we can use the stream function vorticity method. So first statement does not make sense over here. And we can
It
now,
can
second
be.
question, sorry.
So it can be used in either case, right?
It
Laminar.
can
Yeah.
be used, but I have not seen any papers or any relevant information related to usage of such methods in turbulent regime.
Okay. Okay.
But generally speaking, if we write down the equation of Navier-Stokes continuity in the deviational velocity, how we actually solve for turbulent regime flows, is we can use it, the stream function vorticity method.
Okay.
And option 2, it cannot be used because the flow is 3D. Is that statement correct?
Correct.
Actually, it here the question, according that statement may be correct, but in this question we have been given with an axis symmetric flow as shown earlier. So rather than axis symmetric means that we are only dealing with two-dimensional flow.
Yeah.
Therefore, this statement is okay. This statement is wrong over here. This statement is wrong again, because this flow is not 3D, this flow is in fact 2D. And the first statement I made a mistake in saying we can be used because the flow is linear. It's the statement itself is wrong. So the third statement, it cannot be used because because the method can be used only for Cartesian coordinate system. In the lecture, we have also seen the lecture uploaded by sir, we have also seen that we can derive this for an r theta or spherical coordinate system or a cylindrical coordinate system. So option 3 also is wrong. We can convert this into an r theta or a r theta z or r theta phi coordinate system and solve the incompressible flow over here. So none of these statements is correct.
But 3D, if it is 3D flow, it can be used, isn't it? Or no?
Um, Actually, this method only holds true for 2D, right? I
2D.
mean, yeah, we take the curl of the curl of the Navier-Stokes equation, so that the problem becomes we neglect the variation in that variation of pressure, and we solve for the velocities alone. So we generally solve only two-dimensional problems in here while we are doing for stream function vorticity method.
Just a general question. I know I've come across many occasions where we say we take 2D, but in
Hmm.
practically, I mean, where will you get 2D flows? I mean,
Any
yeah.
cylindrical pipe flow such as this
Hmm.
one
Hmm.
that's shown here in the figure, this is a perfect example of a
Okay.
two-dimensional.
Okay.
I mean, we are generally more easily will be able to find two-dimensional flow than an actual three-dimensional problem in general. It's more common to observe a 2D flow than a 3D flow.
So even if it's a rectangular pipe, yeah, or
Even if it's a rectangular
yeah,
pipe, we will be solving only a 2D flow.
hmm,
Like we'll only find the variation of velocity along here as a function of, let's say, let this be y and let this be z. We'll only be finding the velocities of u in as a variation of y and z.
hmm.
Yeah, it is. I mean, it's not that it's uncommon, but it's not that it is rare or something. But yeah, generally we try to simplify our problem by creating a two-dimensional view of it.
Yeah, okay.
Okay, for the state next questions, question number 6. For the steady state axisymmetric incompressible laminar flow case shown in figure 8.1, finally the whole sentence is correct. Which of the following statements is true about the artificial compressibility method? It cannot be used because the flow is laminar. It cannot be used because the flow is state 3D. It cannot be used because the flow is steady. What would be the answer here?
I think all three are wrong. Yeah.
Yeah, all three points that have been given here are in fact wrong. We can use this in laminar flow. We can use the artificial compressibility method for three-dimensional flow, and we can use a steady or the unsteady equation over here. Basically, what we are doing in an artificial compressibility method is to define a pseudo compressibility factor as mentioned in the class, and we call that as rho star, and we solve the continuity equation as 1 minus 1 by beta star dou rho star by dou t plus del dot u is equal to 0, and we define this rho star as rho by beta square, and this rho would be rho star would be the known as the pseudo compressibility factor, and we solve the momentum equation by dou u by dou t plus del dot u equal to 1 minus 1 by rho del p plus mu by rho del square u. So yeah, we can use this for the steady state problem. We can use this if the flow is laminar, and we can use it if the flow is three-dimensional. So all these three statements are in fact found to be wrong. Okay, question number 7. Which of the following methods can be used for the flow shown in figure 8.1? First one, McCormack method. Can we use McCormack method for an incompressible flow through a contraction section of a pipe of circular cross section? The answer would be no. We
No.
can't
Yeah.
use McCormack method here because McCormack method requires a compressible flow, a variation of a density, and we solve for the nonlinear version of it, or the coupled nonlinear version of it, using that. What about pressure equation or pressure equation approach?
Yeah.
Yeah, we can use pressure equation approach, and in fact we can also use pressure correction approach for the solution of incompressible flows, whereas we can only use the McCormack scheme for compressible flow problems, where we can couple them and write them as a single term and then solve them using a two-step predictor corrector method, very similar to a pressure correction approach. Okay, question number 8. The pressure correction approach cannot be used for which of the following? First one is time dependent flows, second one 3D flows, third one viscous flows, fourth one none of the above.
It can be
And
used
the
for
answer,
all. No?
yeah, the pressure correction approach can be used for an unsteady state problem. Let me just start by telling what the pressure correction does. It's a basically, one second, sorry about that. It's basically a finite volume method to solve the Navier-Stokes equation, where we initially guess the pressure and solve to get U star and V star uh, from the equations that were discussed in the lecture, and then we find that these U star and V star won't satisfy the continuity equation. So we substitute back and for to finally end up with a velocity and a pressure field that satisfies the continuity equation and the momentum balance equation. Therefore, we can use this for a 3D flows as well. We can use this for viscous flows as well. So the correct answer is none of the above. We can find out how the variation of the diffusion term or the viscous term in that flow can be incorporated here. Similarly, we can have a three-dimensional flow and an unsteady flow while solving for the pressure correction method. Okay, question number 9, a very straightforward and easy question. Full form of simple is, yeah,
Semi-implicit method.
yeah, it's a semi-implicit method for pressure link equations. So semi-implicit method for pressure linked equations yields the acronym simple. There is also other methods such as let me just write that down, simple C, which is basically simple corrected, and there is uh, simpler, which is simple revised, There is SMAC, which is basically simplified marker and cell. This is based on the people who discovered this. There are also other methods like simplest and so on. Okay, moving on to the last question of the graded assignments for the previous week. A staggered grid system is it to used for enable treatment of flow domains of irregular shape, to simplify grid generation, to eliminate checkerboard oscillations in pressure, or to check the overcome the stability problem.
C.
Yes, the staggered grid system is used to eliminate the checkerboard oscillations in pressure. Where if we use a collocated grid or a checkerboard grid, where we find the positions of we find the pressure in the pressure velocity and pressure and the two velocities in the same grid, we will not be able to find a gradient in the pressure variation. Therefore, if we find the pressure over here, we generally find the u velocity over here and the y velocity over here. Similarly, we'll get a grid like as shown in the lecture as well. So this type of grid is called a staggered grid system, where we find the velocity at I plus half and the u velocity at I plus half and the v velocity at uh, j plus half, or j plus n by 2, or whatever it is, and we find the pressure at the I and j. We'll take a couple of minutes break here and come back to the ungraded assignments or non-graded assignments for the week 8 after in a couple of minutes. Okay, I hope everyone's back. Let's resume for solving the non-graded assignments for week 8. Looking at the first question, for the three-dimensional incompressible flows, the minimum number of partial differential equations to be solved is. Please know that this is a three-dimensional flow and incompressible flow. So
Four.
yeah,
Five.
we,
Five, no?
no, we need, no, the answer is 4, right?
The
So we
temperature.
will,
Hmm.
no,
Sorry.
we don't have to worry about temperature over here. So I'll come to that. So we would need to solve an equation to find out the pressure, u velocity, or the velocity components, which has u, v, and w as a vector, the velocity vector. So basically, we are supposed to find 1, 2, 3, 4 for flow problem. We are not worried about the changes of temperature. We do not consider the function of temperature or any other variations such as density for an incompressible flow problem. We worry about temperature when it is explicitly mentioned there is a need to measure the temperature. So other than that, we just generally solved for pressure and the three components of velocity for a three-dimensional incompressible flow problem. So the correct answer is 4, which comes from one from, as I had said earlier, one from the continuity and 3 from the Navier-Stokes equation. I hope that answers that question that was there. Okay, moving on to question number 2. Which of the following is a characteristic feature of the artificial compressibility approach to solving Navier-Stokes equation? First one, pressure need not be evaluated. Second one, can be applied to unsteady flows. Third one, cannot be applied to three-dimensional flows. What is the correct answer here?
2.
Yeah, it is only two, because pressure, we have to evaluate pressure while we are solving for the artificial compressibility factor, and uh, we can apply this to three-dimensional flows. The only correct answer is can be applied to unsteady flows as well. Next, which of the following variables are evaluated at the same location in a staggered grid? So while I was talking about the staggered grid, I was pointing out where the circle indicates the pressure, the X indicates the U, and the triangle indicates the V. So if we measure the pressure at the center of this area, we measure the V velocity over here, U velocity here, V here, U here. Similarly, the next board will have a pattern that comes out like so. So what we intend to measure is the pressure and temperature at the center of the cell, which are done together, whereas the U and V are measured at I plus half and j plus half of the ith and jth point, where pressure or temperature is evaluated. Since these are in fact functions of not vector functions, we avoid checkerboard pressure oscillations just by changing the positions of the velocities by measuring them at a cell that is half distance apart in the x and y direction. Alright, moving on to question number 4. Which of the following methods requires an equation of state?
3.
Actually, it's both 3 and 2. The stream function vorticity method does not involve the use of does not use the pressure evaluation of pressure, or does not involve require use of equation of state, because in stream function vorticity method we I'll just call that
Eliminate
as,
pressure, right?
yeah, we neglect pressure and find velocity field, and then we find pressure by putting or substituting in the Poisson equation. Whereas in artificial compressibility method, we require an equation of state to find the pressure at all points in the field. And as we have seen last week, McCormack method, which finds out the position or finds out the variation of density as a function of uh, let me just put it as x vector, so position vector or time, and we solve that and we find pressure by equating by using an EOS, which relates pressure as a function of density and temperature. Therefore, both artificial compressibility and McCormack scheme use the equation of state to find the pressure.
Can you explain that first part? How we find pressure by using the Poisson equation?
So we have the velocity field across. Let me say that this is a field in study. We have the velocity at each and every point over here, right? So we can use what do you say? A simple since we have the variation of velocity along all these points, we can find that out there. I'm not exactly sure how we can find out, but I just turned out that we can use the Poisson equation to find the pressure. I may have to take another look at it to further elucidate on this point.
Yeah, okay.
So basically we know that the gradient of pressure can be found out over here, and then we take the double gradient over here, or the sorry, the divergence of the gradient over here to find out the variation of pressure in this field. I'll just take another look into it about how to find pressure
Yeah, sure,
from
sure. Yeah,
the equation, from the Poisson equation, maybe next time.
sure.
Okay, I guess we have completed the graded and non-graded questions for the previous week, week number 8. I have an example question. Since we have almost an hour time left, I thought we can do one of the example questions that was under discussion in week 3. And this does not come in the syllabus that is being discussed, which deals with the solution of computationally solving or numerically solving such problems. So officially, at least, or technically, if you have any other doubts, I'll be willing to discuss. But till now, we have completed the questions that I have prepared for week number 8. We'll be going back and solving an analytical, finding out an analytical method to solve one of the equations which we have already numerically solved.
This is there in the. You have already discussed this in one of the earlier lectures.
No, no, no. I have not done this before, so I
Okay.
will be doing this from today again,
Okay.
or starting a new topic. This is not part of the syllabus. This is just an additional information that I wanted to share, that I found interesting while I was solving CFD, and to analytically derive the expression also.
Sure.
Okay, let us take a quick look at the question first. Consider the pressure-driven flow in a rectangular channel as shown in the figure. Derive an analytical expression for the case of a steady, incompressible, fully developed laminar flow of a Newtonian fluid. So what we have is a rectangular channel. Let's give it some names now. So let us assume that since I'll also change the coordinates as not shown here, since all the derivation I have done in my work is basically to consider this as the x coordinate, this as the z coordinate, and this as the y coordinate. Let us now define a length scale in the y direction as 2h, such that the center of it divides it as plus h and minus h over here. Similarly, let us give a characteristic dimension in the z coordinate as 2 times b, which again the center of the flow divides it into as plus b and minus b. Let us assume that the velocity is in this direction. Regardless of what the picture says, let us again disregard this again over again. Let us assume that the fluid velocity u is in this direction, and as we can see here, we have already discussed how to bring down the Navier-Stokes equation into a simpler format. Let us take a look at that, what we did. First we wrote down what the Navier-Stokes equation was: dou u by dou t plus del dot uu is equal to minus 1 by rho del p plus mu by rho del square u. We can assume a few things over here. So what have they given us is that it is a symmetric rectangular channel, symmetric along the axis of what the study has been. uh, so let us first neglect the three-dimensionality of the problem and assume that we are in fact dealing with, or we are in fact, let me finding only u and neglecting uh, the velocity in the y direction and velocity in the z direction, v and w. So therefore I can bring down the Navier-Stokes equation as dou u by dou t plus del dot u square is equal to, or if you have to write this in a u dou u by dou x is equal to minus 1 by rho del p plus nu, again if it's in a dou p by dou x plus mu by rho dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. A few more assumptions have already been given over here, where we can assume a steady state problem and an incompressible fully developed laminar flow. So we can neglect this term due to the fact that it is a steady state problem. We can also neglect the variation of u in the x direction and only consider the variation of u in the y and z direction, since this is a fully developed flow problem. So we can neglect this term, we can neglect this term and neglect this term, and also this term, since u is not a function of x. Therefore we can get the final expression as mu times dou square u by dou y square plus dou square u by dou z square is equal to 1 by rho dou p by dou x. Now we have the variation of u in the y and z direction, the pressure in the x direction, and if you know that for a fully developed flow, pressure gradient is constant, so we can also make that statement that this dou p by dou x is a constant and does not vary with respect to any other terms in discussion. And we have already seen how to solve such a problem by using again this one by rho won't be there. We have already seen how to use numerical techniques to find out the answer for this such a flow field, where we use finite difference method or whatever method to find out the velocity at ith point or ith cell, finite volume method if you are using for ith cell, finite difference method if you are finding for ith and jth points, and find out how it varies with respect to pressure. We have already done certain problems in this context. Now let us just take a look how to find this solution analytically. Once again, I just wanted to emphasize that this part is not for any of the CFD simulation or CFD topics that are undergoing discussion. I am just putting it forward as an interesting topic. Sorry about that. Okay, so let's get back to the question that we have. So mu dou square u by
We
dou
can
y
take mu.
square.
We can take mu to the right side also, right? And so the whole thing becomes constant.
Yeah, sure. We can do it like that as per your convenience. We can also take 1 by mu dou p by dou x, so that the entire RHS becomes constant. Yeah. Now, how do we solve this analytically? If have you ever gone through such a problem in any of the courses or any of the works we have done?
Not me. I graduated 40 years ago.
I see. What about the other member? Ridik. Are you there on the call? Would you like to answer?
Yes, no, I'm not really sure about it. So you
Okay,
can go ahead.
fine.
Yeah.
So yeah, sure. So I'll be giving a quick thorough. I'll just start out this problem. see if we can able to complete it, and otherwise we'll be moving on. We'll just keep it on hold and move it to the next lecture, because this solution of this involves a lot of time and a lot of effort and a lot of understanding, basically mathematical understanding. So first let me understand what my problem is. I have second. Okay, let us be this is my, yeah, I have very bad drawing skills over here. Okay, let us assume that I am, this is a square or a rectangular duct that is under question. So I have to find a flow field through this duct, whether in this direction or whatever. I have to find a flow field as a function of the other coordinates y and z, which is at a distance of plus h and minus h apart, and here it be plus b and minus b apart. What is generally done is we assume that one of the coordinates is completely absent. So we generally tend to find out the solution of uh, such a case u. Let us assume that u actual, by incorporating or by what do you say, decoupling this into two fragments, where we solve for a general solution as we have solved a second order ordinary differential equation and a particular solution. We have in maths, how do we solve a second order ODE? We construct a general solution and a particular solution, and the particular solution finds the answer of the homogeneous or non-homogeneous part, whereas the general solution finds the solution of a homogeneous part. If you are unable to follow, please stop me and I am happy to re-explain.
Yeah, but that's in the case of
Ordinary.
one independent
Yeah.
variable, right?
Suppose we
Yeah,
have a problem like d square f by dx square plus a1 df by dx plus
right.
f is equal to g of x. This is
X,
said to be a non-homogeneous function.
right.
Similarly, we solve or we put the same idea into solving such a system of partial differential equation, where we say that u general solution is just a function of y and not a function of z, whereas a u particular solution will be a function of y and z. So basically what I am saying here is the actual solution that I have is a solution in y along with an error term that comes from the boundary conditions of z. So I'll just remake that statement. Solution of u is the sum of the solution of a general method plus the solution of an error term coming from z. I hope this makes sense. So when I actually find out the velocity of u, I am actually finding out the velocity of g plus velocity of particular solution. And as I said before, yes, ug is just a function of y and not a function of z. So therefore we can rewrite, let me call this as equation 1. I can rewrite equation 1 for ug, or the general solution, as dou square. We can, since this is only a function of u, we can write as d square u by dy square is equal to 1 by mu dp by dx. Is there any questions here?
Yeah, whole equal to constant.
Yeah.
Correct. Yeah.
Now we have seen how this question can be solved in our fluid mechanics course. This is basically we are solving for a parallel plate setup. or a pressure driven flow between two parallel plates. So if I have to draw a figure over here, I would have something like this, where this is the y, this is the z, and this is the velocity. So a variation of the velocity in the u direction will only be affected by the two boundaries at the in the y coordinate, that is at a distance of minus h and plus h. Therefore we can solve this equation du by integrate this once, du by dy equal to y by mu dp by dx plus c1. Again integrating this expression, I'll get u by u is equal to y square by 2 mu dp by dx plus c1x plus c2. Now what boundary conditions, again I am solving only for g here, what boundary conditions can
That
I
should
use for g?
that should be C1y, yeah?
Sorry, again c1y plus c2. So what boundary conditions can I use here?
The wall.
Yeah. So totally how many boundary conditions do I need in the first place?
2.
I need two boundary conditions because there are two constants that arises from the second order equation in U. So I require two boundary conditions, and one of the boundary conditions I can use is as one of the answers that was said before is the wall. And what happens at the wall?
U is 0.
Yeah, it's called as the no slip
No slip.
condition. Yeah, ug should be equal to 0 at y equal to plus or minus h. But this, even though this boundary is given at two locations plus h and minus h, we can't use them because they are redundant. Even if we use it at plus h or minus h, we can only find one of the constants here. So what is the second boundary conditions that is required over here?
Slope is, du by dy.
Du by dy,
Um,
at which, how do you, yeah,
will be
go ahead. I think you are correct only.
du by dy
Huh.
should be 0, no? At the wall also.
At the wall it need
No,
not be zero. So
no,
when
no.
let me just zoom
Or
in on this area over here. So I'm getting a parallel plate setup over here. So the velocity, let me have zoomed in like into 100 times. I'm just looking at this particular region over here. So when I zoom in over here, what I'm gonna get is there will be a velocity here, u velocity like this, and there will be a u velocity like this. So in fact there won't be any velocity over here. So there will be a du by dy at plus or minus h will not be equal
yeah,
to
yeah,
0.
yeah.
So where do we get this gradient to be 0? The correct answer, the statement is correct. Du by dy will be 0, but where will it be 0? Ritik, do you like to answer if you have already solved this problem, such a problem in fluid mechanics?
I haven't solved such a problem, but I think in the middle, yes.
Why would it be middle 0 at the middle?
Uh,
No viscous effects.
Yeah, exactly. This is known as stress-free boundary condition at the uh, center uh, of the problem. So this comes up because the flow is symmetric along y. So whether it is at plus h and minus h, y is the velocity profile is symmetric along the vertical axis that is being discussed over here. So therefore we'll get dug by dy at y equal to 0 is in fact 0. And therefore when we solve such a problem, we'll get ug is equal to, let us take the second boundary condition first, where we defined dug by dy at y equal to 0 to be 0. and substitute here in this equation, what will we get as C1? Any answers?
So it will be negative of h, what is that? Yeah, plus h by mu dp by dx.
No, no. I'm putting the second boundary condition over here.
Yeah, that's right. So
Yeah. So
so
C1.
negative. Yeah. So C1
Sorry.
becomes negative of h
Negative of.
h that h by
No, this
mu
is
dp.
y over here, right?
Yeah, but that becomes h, right?
No, that becomes 0.
Oh, I'm sorry. Oh, I'm sorry. Oh, C1 0 then. Okay.
Yeah, exactly my point I
Right.
wanted to
I'm
make.
sorry. Yeah.
Yeah. So C1 will be 0, and we'll get by substituting the second point over here, the second boundary, the no slip condition in the final expression for UG, we'll get C2 to B. Can anyone tell me the answer?
That will be the negative h squared
Yeah, it'll be minus, oh,
by 2. Yeah.
minus h square by 2 mu dp by dx.
Yeah.
Therefore, when I write them together to find out what the velocity profile is, I'll just directly simplify and write. Please tell me if you are able to follow this. I'll get h square by 2 mu dp by dx into 1 minus y square by h square. Please let me know if you are able to get this or not get this.
Yeah. This is 1D flow.
Yes, this is a flow in the x direction as a function of the y coordinate. So basically what I'll be getting is, if this is x and this is y, I should be getting a parabolic profile over here, where the magnitude of u is shown as the arrows and the direction also is represented in there. The magnitude is shown as the distance in the length of the arrows, and the direction in the the arrows. Yeah. Similarly, if I take the gradient of u, I'll get it like in this direction. So at this is du by dy. So here it will be positive and here it will be negative with a 0 at the center. That's why our stress-free boundary condition comes over here. I hope what I have explained till now makes perfect sense.
Yeah.
Okay, so we have found out what UG is, or the general solution is, which is the pressure driven flow for between two parallel plates. Now let us find out what the correction or particular solution is by incorporating the effect of velocity of the next segment over here. So before we start that, we need to find out how our boundary condition and governing equation for UP looks like. We know that the boundary condition for U actual, which will be equal to minus dp by dx plus, or let me write it as minus 1 by mu dp by dx dou square ua by dou x square plus, sorry, this would be y square dou square ua by dou z square is equal to 0. This we have already established. We can just turn the notes and see that. And for general solution, we wrote this as minus 1 by mu dp by dx plus d square ug by dy square is equal to 0. So we know that the actual solution will be general solution plus particular solution. Therefore, we can write U particular solution to be U actual solution minus U general solution. And since this problem is a linear problem, we are dealing with linear governing equations. When we solve for UA and UG by using the governing equation and the boundary condition shown here, we should expect uh, we should expect the particular solution to also follow the governing equation, or we can say that equation, let me call this as equation 1. Okay, I already called it as equation 1, so I'll just call this as equation 2 and equation 3. If I subtract equation 2 from 3, I should be getting an equation, a governing equation for UP. Does that make sense?
Yeah, that's how we have defined it anyway.
Yeah, exactly. So we have just defined it like that. So when I subtract equation 2 from 3, equation 2 minus equation 3, I'll see that the pressure term goes away. This is basically the homogeneous part of, non-homogeneous part of the equation, which goes away, and we solve the rest of it by subtracting dou square u minus dou y square minus, so I'll just write it down. I can write this as, this term will anyway get cancelled out. Let me just, yeah, this is fine. This term will get cancelled out, and I'll be writing it as dou square ua by dou y square minus, just for simplicity or sake of understanding, I'll just write it as dou square ug by dou y square. But regardless, ug is just a function of y, plus dou square ua by dou z square minus dou square ug by dou z square. We know that this second term or the last term in this expression is 0. So I'm just writing it down just for the sake of what do you say, adjustment. I'll just show that step right now. So when I make such a statement over here, when this entire thing can be rewritten over here as dou square up by dou y square plus dou square up by dou z square should be equal to 0. I hope this makes sense. Ridik, are you able to follow?
Yes, more or less, yeah.
Okay. Please let me know if you have any doubts. Mr. Sridhar, are you able to follow this?
Yeah, can you just go back a little bit? Just up. Yeah, over here. So the first one is del squared UA. So these two terms are UA, right? In
Yes,
equation 2.
yes, yes, yes.
And this is UG, correct?
Yes,
On
yes, yes,
3.
yes.
So we are just subtracting 2 minus 3.
Yes.
So you'll get UAY, UAZ minus UGY, correct? Yeah, okay. So one of these goes away, no? 2 minus 3 here, which you've shown below.
None of this gets cancelled out. Only thing gets cancelled out is the pressure term.
No, but there are only 3 terms, no?
Yeah,
2 and 3.
I
Yeah.
have added a dou square ug by dou z square. Although it does not vary with respect to z, I've just added that over here.
Okay, okay. But that's 0 in any case.
Yes.
Okay.
Just to make sure that I get the particular
I got it.
solution.
I got it.
Yeah. So I have the governing equation for the particular solution. Again, just as how I have described the governing equation for the particular solution, I'm going to do that for the boundary condition for the particular solution. So let me start by defining, before I go to define how to do the boundary condition for the particular solution, we have already seen how the boundary condition for, what do you say, this one. This is UG, boundary conditions for UG is already discussed, but I have not yet told about how the boundary conditions for UA would come out. So before we go on to describe the boundary conditions for UG, let me quickly tell how the boundary conditions for UA comes out. So, so what are the boundary conditions? How many boundary conditions would we need in total for solving the governing equation for UA in equation 2?
2. No?
It's not 2, or
Oh,
it's
I'm
not
sorry.
exactly 2. We would need two boundary conditions in Y
And 2
and
here.
two
Yeah.
boundary conditions in Z.
Yeah.
So therefore, we would need a total of 4 boundary
Yeah.
conditions. And what would they be?
The wall conditions.
Yeah, it will be very similar to what we have done for
Yeah.
the general solution.
And the
That
slope.
is,
Yeah. Yeah.
yeah, no slip at walls, and I'll write them as 1 and 2, which should be u at y equal to plus or minus h should be equal to 0, u at y or
Z.
z equal to, sorry, z equal to plus or minus b should be equal to 0. And the second and the third and fourth would be the stress free condition at the center, and that is dou u by dou y at y equal to 0 should be equal to 0, and the fourth one is dou u by dou z at z equal to 0 should be 0. So these are the boundary conditions for UA. We have not yet started for UG. So let us go ahead and find out the boundary conditions for UG based on UA and UP. So as we have defined earlier, there will be 4 points to consider: y equal to plus or minus h, y equal to 0, just leave some space over here. So y equal to 0, z equal to plus or minus b, and z equal to 0. So let me write down the boundary conditions for UA. What is the value of UA at plus or minus h?
0.
0. And what about the, one second, yeah, this will be fine. I'll keep some space here. Okay. So what is the boundary condition for the particular solution at, sorry, general solution at y equal to plus or minus h?
Same.
Yeah. Therefore, the particular solution will be the boundary condition for particular solution will be boundary condition for actual solution minus the boundary condition for the general solution, which will in fact be
0.
0. What about the boundary condition? What about the condition at y equal to 0? We
Right.
know that dua by dy
Yeah.
should be equal to 0.
0.
Similarly, dug by dy should be equal to 0, and dup by dy should also be equal to 0. Right? But let us take a look at interesting things happen here when we take a look at the boundary conditions for z. What happens to the boundary conditions for UA at plus or minus b?
0.
It's 0. And what happens to the derivative of UA at z equal to 0?
Z equal to 0.
Yeah, we have defined at the fourth point over here.
Oh, okay.
Okay, that means I have not written A anywhere over here. I just noticed that. So this will be again 0. Right? So when we find out the general solution, we have not talked about what the what the velocity is going to be at a position b distance away from the origin. Therefore, we cannot say anything about the variation or the general solution at plus or minus b anywhere. So, the solution at z plus or minus b must be following the value we have found out as per the equation shown here. Let me call that as equation number 4. Therefore, at plus or minus b, ug must be minus dp by dx. It will be h square by 2 mu 1 minus y by h square. Does this make sense?
So y becomes so
Okay.
what's the value of y? Yeah.
Yeah, so my point I want to make here is that the general solution that we have solved contains only the variation in the y direction over here.
Yeah.
So suppose I am introducing a constraint over here, an imaginary wall over here, and I am measuring the velocity at the center of this wall. What would that velocity be? It would be following the final expression of velocity over here. That's all I'm saying. Does
Oh,
that make sense?
that's because the gradient is 0 for
That's because there is no variation of
yeah,
the general solution in the z
z.
direction.
Yeah.
All right. What about at z equal to 0? At z equal to 0, we cannot say anything. Again, we cannot say anything. But what can we find out from the equation number 4 shown over here? What is dug by, okay, this would be, yeah, this is fine. One second. So, since we have not mentioned ug as a function of z, the derivative of ug will also be 0 with respect to the z. Does this make sense? Since I'll just explain it based on the equation I've shown here. Is there ug is not a function of z, therefore dug by dz should be equal to 0. That's all I'm saying here.
Okay. That
All right.
applies everywhere, yeah.
Sorry?
That applies the entire
It doesn't matter where it's applied.
yeah,
This statement applies everywhere,
everywhere, yeah.
but we are only looking at z equal to 0 at the center.
Correct, yeah.
Although this equation is valid everywhere, we are only looking at the center right now. Now, based on these two statements, how can we write the boundary conditions for the particular solution? What will be the boundary condition at z equal to plus or minus b? We know that the particular solution, or we can write that the actual solution is general solution plus particular solution, which means that the particular solution must be actual solution minus general solution. Therefore, the particular solution at any point must be equal to the actual solution at any point minus the general solution at the any point. And also it also implies that the derivative of the function at any point with respect to y or z should be equal to the derivative of the actual function y or z minus dug by dy or z. So what would be the boundary condition for z equal to plus or minus b for particular solution?
That minus of, so that becomes a plus.
Yeah, so
So
it would
yeah,
in fact be negative of the terms shown here in the
yeah,
ug,
Yeah.
which would in fact be dp by dx h square by 2 mu 1 minus y square by h square. And what about the value at dup by dz at z equal to 0?
That is 0.
Again, that would be 0. Okay, so I have established 4 boundary conditions and the governing equation for uh, the particular solution, and already solved the equation for general solution. All I need to do is solve for the particular solution as well.
So we are applying uh, this principle that actual is equal to general plus particular for boundary conditions is because boundary conditions satisfy the direct for the differential equations themselves, correct?
Yes, 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 exactly.
Right.
And we are able to do such a statement because of the linearity in the problem that we are discussing.
Okay.
If we have to incorporate a convective or another term in this setup, we can't go through this method, because that would incorporate that we have to take into account the non-linearity as well.
Yeah, there are no known solutions to that, isn't it? Or are there
I
analytical?
think it's better to do those kind of problems numerically. Even this requires a lot of effort analytically solving it, right?
Yeah, yeah,
It's not quite easy.
correct.
Yeah.
Yeah, this is
Ritik,
linear, so yeah.
yeah, exactly. Are you able to follow, Ritik?
Yes, yes, I am able to follow. Thank you.
Oh, all right, cool. So let me go back to where I was, where I derived the equation for the governing equation for up as dou square u by dou y square plus dou square u by dou z square is equal to 0. And the 4 boundary conditions that come up are these 4. Yeah, this is the governing equation for particular solution. This is the boundary condition for the particular solution again. Okay, I'll just, again, I should write the p over here, otherwise we'll get confused. Right over there. Fine. Okay. If you know how to solve such an equation, you can suggest what would be the best way to start.
Just like you did in the first case.
No, we
Oh,
have already found out
found
the
that.
governing equation, right? We have already reached the governing equation and the boundary condition. And in the first case, we have not yet solved the actual solution. We are yet to find out. So we have not solved it actually.
So maybe define a new del u by del y as something and del u by del z as something.
It will be difficult or tedious to go that route, but I think a part of that what you said makes sense. We have to define, or we have to re-represent this u particular solution as the product of two solutions, let's say f and g, wherein f is only a function of y, g is only a function of z. And this procedure, I think if I say the name, you would be able to familiarize yourself with it, is called as
Separation of variables. Huh?
separation of variables. What we have assumed here is that the variation of v, or a variation of the particular solution along y, is independent of the variation of particular solution along z. Therefore, u as a function of up as a function of y and z can be decoupled and written down as a function of y times a function of z. And this kind of separation is called as this kind of method is called as the separation of variable method for solution of partial differential equations. Okay, therefore I can write this above equation number, let's call that, I think, 5, as dou square fg by dou y square plus dou square fg by dou z square is equal to 0. This is not d, this is dou z square. Now we know that f is only a function of y, g is only a function of z. Therefore, this equation becomes,
Maybe you should write, I think, del squared f by del y squared plus del
yes,
squared g
g
by.
times d square dou square f by dou y square plus f times dou square g by dou, again this is not d, this is dou z square should be equal to 0. A little bit of simplification from the notation is g f double dash plus f g double dash should be equal to 0. Although the derivative of f is in y, the derivative of g is in z. Please make a note of that. And I am just rearranging this to write g f double dash is equal to minus f g double dash, and f double dash by f is equal to minus g double dash by g. So what I have obtained here over here in this equation is that the second derivative, the f double dash by f, that is the variation of f in the y and variation of g in the z, or the differentiation, the second differential of f and g is coming out to be same. That means that the only way this equation f double dash by f equal to minus g double dash by g can hold true if
Equal
this
to
is
constant.
constant.
Yeah.
Exactly. Have you solved any such problems?
Uh, a long time ago.
I see. So yeah, we can write this statement if and only if f double dash by f equal to minus d double dash by g, and we can equate that to a constant, because such a setup can only be equated if constant is the only outcome. If it is a function of y or a function of z, this cannot happen. Therefore, what constant do we use? The next question comes, what constant do we use? Do we use a positive constant, a negative constant, or 0? Okay, let us assume that we have taken let me call that constant as lambda square. If it's a positive constant, I'll call it as positive lambda square. If it's a negative constant, I'll call it as negative lambda square. If it is 0, I'll just call it as 0. I hope this part makes sense.
Why would you even think of zero?
We can also get a constant as 0, right? I mean, this can also be equated to 0. That also makes sense. If the second derivative of f and second derivative of g is 0, then we can also say that this statement holds true. But we'll come to that. We'll come to whether it can be 0 or not based on the physical significance of it, by equating f double dash by f equal to minus. We'll just take each case by the way then. Case 1, equate it to 0. Therefore, f double dash by f should be equal to minus g double dash by g should be equal to 0. Therefore, we'll get f double dash equal to 0, g double dash equal to 0. Therefore, we'll get f is a function of, let's call that c1y plus c2, just by integrating this twice. G is c3y plus c4. Now we know that since we have split u as a function of y and z, f of y and g of z, whatever boundary conditions we have for up as y should hold true for f. Whatever boundary conditions we have for z should hold true for g. Therefore, if I have such a setup, and if I am getting that y at plus or minus h is 0 and z at plus or minus b is some function of y, let me substitute y at equal to plus or minus h. I'll get f as or f should be equal to 0 is to be equal to c1 times plus or minus h plus c2, which means that c1 is equal to, or plus or minus h times c1 should be equal to c2. Similarly, from this, from this boundary condition y equal to 0, dup by dy equal to 0, I'll get c2, or I'll just rewrite that, df by dy should be equal to c2 should be equal to 0, since dup by dy, or this is not call it as dou up by dou y at y equal to 0 should be equal to 0. Therefore, I got c2 as 0, and if I substitute in the previous equation, I'll get c1 as 0. Did I go too fast? Ridik, are you able to follow?
No, yes, I'm able to follow, no worries.
And Mr. Sridhar, any doubts over here?
I think you went a little fast.
Okay, so all I've done is, if I assumed f double dash by f to be 0, and so therefore I'll get f double dash to be 0. Therefore, I just integrated this twice. F double dash equal to 0 implies that f dash is equal to c1 and f is equal to c1y plus c2. And I substituted y equal to plus or minus h, the boundary condition for up to be substituted for f, and the boundary condition for up is y equal to plus or minus h, and this one, and dup by dou y at y equal to 0 equal to 0. So when I just put the equation of y equal to plus or minus h, I'll get c1 plus or minus h times c1 equal to c2, and when I use the second boundary condition, I'll get c2 to be equal to 0, since this statement is correct, and if double dash is equal to c1.
Fine. Yeah, got it.
c1 equal to c2 equal to 0. Are you able to follow this now?
Yeah.
Okay. So we have found out that if we put c1 and c2, if we put the equation equal to 0, we will get c1 and c2 to be equal to 0. Therefore, this is something known as a trivial solution and does not hold good here. Therefore, we have to now substitute whether case 2, whether we can substitute minus lambda square here. So let me put the equation for minus lambda square here and see whether I'll get f double dash by f is equal to minus g double dash by g is equal to minus lambda square. Let me just equate this one first, where f double dash by f is equal to minus lambda square, or f double dash is equal to minus lambda square f double dash plus lambda square f equal to 0. What would be the solution over here?
Oh, this we got to use the characteristic equation.
Exactly. So this would be the d square f by dy square plus lambda square f equal to 0. Therefore, d square plus lambda square times f is equal to 0. I hope you would be able to recollect some of this from engineering mathematics.
Yes.
So therefore, we solve that d equal to plus or minus I lambda. And what is the solution when the complex roots are obtained for d?
E raised to
It's not the exponential one.
uh,
Okay, okay, Ridik, do you know?
No, sorry.
Okay, so if d is plus or minus I lambda, or in fact, if complex roots are obtained for d, we'll get it as alpha plus or minus I beta. Then the solution should be e raised to alpha x, or in this case alpha y, cos beta y plus sin beta y. Therefore, what is alpha here? Alpha is 0 here. So e raised to 0 times y should be 1, and this, the rest, beta here is lambda. Therefore, I'll get cos lambda y. Just 1 second, please hold. Lambda. Yeah, okay, sorry. So it will be cos lambda y plus sin lambda y.
Why did you put that one there? Y
E
equal to
raised to
0.
alpha y, right? Alpha is
Oh,
0.
oh, alpha 0. Okay. Okay.
So I'll get f as cos lambda y plus sin lambda y. Actually, when we solve it this way, we'll get the correct answer. So just one step, I'll take a detour over here, and I'll show how case 2 or case 3 of putting plus lambda square does not make sense. When we solve it this way, we will find that the answer makes sense. But before that, I wanted to make sure why putting plus lambda square does not make sense. So we'll be putting f double dash by f is equal to minus g double dash by g equal to plus lambda square. Therefore, f double dash is equal to lambda square f, and we'll get f double dash minus lambda square f should be equal to 0, where we can write this as d square f by dy square minus lambda square f should be equal to 0. D square minus lambda square times f should be equal to 0. So d should be equal to plus or minus lambda. A solution with this particular root will have the equation of c1 e raised to lambda y plus c2 e raised to minus lambda y. I forgot to put c1 cos x and c2 sin x. This will also have c1 and c2 here, c1 and c2 here. Yeah. I think I may move a little bit fast here. I'm
No, I'm with
hoping.
you. I'm
All
with
right,
you.
all right. Ritik, any doubts?
Me too, I'm with you. No worries.
Okay.
Going
So
strong.
okay, f is equal to c1 e raised to lambda y plus c2 e raised to minus lambda y is shown here. Now, if I put the boundary conditions of f, where I need y equal to plus or minus h, f to be equal to 0, and y equal to 0, I need f to be, or df by dy to be equal to 0. This is the two boundary conditions that we have defined for y, for f, sorry, yeah. So f is only a function of y, where y at plus or minus h should be 0, and y equal to 0, df by dy should be 0. That's exactly what I have written here. Y equal to plus or minus h, f should be 0, y equal to 0, df by dy should be 0. Therefore, I am trying to substitute the value of plus or minus h into the first equation. I'll put this over here. I'll get c1 e raised to lambda h plus c2 e raised to lambda times minus lambda h. You can assume to be plus or minus h here, that doesn't matter. And here as well, plus or minus h to be equal to 0. Whereas if I differentiate this once, I'll get c1 lambda e raised to lambda times 0. This is at y equal to 0. So plus c2 lambda e raised to uh, lambda times, or minus lambda times 0 should be equal to 0. Therefore, from equation 1, I'll get c1 e raised to, let's say, plus or minus lambda h plus c2 e raised to minus or plus lambda h should be equal to 0. and here I'll get C1 plus C2 equal to 0, or lambda C, it doesn't matter, lambda will anyway go away. I hope you're following this. Any doubts?
No, I'm okay.
Okay, so what is the value of C1 and C2 over here? The only value C1 and C2 can have is 0, because
It's
these are
zero.
two
Yeah.
yeah,
Yeah.
linear algebraic unrelated equations, or independent equations. Therefore, only way this will have a solution is when C1 and C2 are 0, which will again lead to our previous argument that this is a trivial solution and therefore does not hold good. Okay, now moving on to what we were discussing earlier. Let me call, one second, let me call this as case 3 and the earlier one as case 2. It doesn't matter, but yeah, I'll just, so that for the sake of continuity, case 3 will be this, where we solved, equated it to minus lambda square f double dash by f equal to minus g double dash by d equal to minus lambda square, and we found out f as a function of c1 cos lambda y plus c2 sin lambda y.
We apply the
Now,
same BCs again. Yeah.
yeah, we apply the same boundary condition of y equal to 0, f should be, sorry, y equal to plus minus h, f should be 0, y equal to 0, df by dy should be equal to 0. Alright, we substitute these boundary conditions one by one. First, we'll put the first one over here. We'll get c1 cos lambda h. I'm just putting plus h over here for the sake of simplicity. It doesn't matter if it's plus h minus h, we'll get the same answer. C2 times sine lambda h should be equal to 0. This will be equation number 1. If I put equation number 2, I'll get C1, minus C1 lambda sine lambda times 0 plus C2 lambda cos lambda times 0 should be equal to 0. Please let me know if you are following this.
Got it.
Okay, so we'll get this term to be 0, whereas this term does not go to 0. So we'll get C2 lambda cos, that
would be 1.
Yeah, C2 lambda cos lambda, C2 lambda should be equal to 0, or I'll get C2 to be equal to 0. Substituting for C2 in, not call this as equation 1, there are too many equation 1s here, I'll call this as equation A. Substituting for C2 in equation A, we'll get C1 cos lambda h is equal to 0. Now, we can either write C1 equal to 0, or we can write cos lambda h to be equal to 0. If we write C1 equal to 0, we'll again get a trivial solution where both C1 and C2 are 0. Therefore, we can't go this way. So, we have to obtain where cos lambda h to be 0. And when does cos lambda h to be 0?
When lambda h is equal to pi by 2.
Yeah, or it can be pi by 2, it can be 3 pi by 2, it can
Yeah.
be 5 pi by 2, any value. That means it has to be 2n plus 1 multiple of pi by 2, where n goes from 0, 1, 2, 3, etc. If n equal to 0, we'll get pi by 2, n equal to 1, we'll get 3 pi by 2, etc.
Yeah.
And therefore, if lambda is equal to 2n plus 1 pi by 2h, we'll get a solution, is what I'm trying to say. Okay, and this solution will be a summation of all the solutions of this lambda. And here what we'll do is we'll do something known as Fourier cosine series, where we have lambda n that's going from 0 to infinity. So therefore the solution of this problem will be the summation of all the terms that goes from 0 to infinity. It won't be just 1 0, it won't be just the value at pi by 2 or just the value at 3 pi by 2. It will be a weighted average of all the sums, all the solutions that goes from n from 0 to infinity. Therefore I can write this as f is equal to a naught plus sigma n is equal to 1 to infinity uh, an cos lambda n times y, where an basically what I've done is just remade this c1 into an a1. Basically that constant remains as constant, but I'm just saying that okay, I can actually, let me just remake this rather than to avoid confusion. I'll just remake this as n equal to 1 to infinity an cos lambda n times y. This is known as a Fourier cosine series in an and lambda n. We can find the value of an by taking the minus h to plus h a the function of y with respect to lambda n cos lambda n y by integral minus h to h cos lambda n y times cos lambda n y. This is dy, again dy.
Oh,
Okay,
this is all part of Fourier series, huh?
yeah, this is all part of Fourier series analysis. So I guess I think I'll stop here and continue the derive. Just a couple of more steps are only required, but I think I'll stop here right now. So maybe you can take a look at how we have derived this equation up until maybe say this point where we have written down an expression for lambda n. I'll explain this part of explaining the writing down the Fourier cosine series in this terms in the next class only.
Sure.
Otherwise it will be too much. Again I have to continue 1 or 2 more pages of derivation. So
No
we
problem.
can see why the analytical solution of such a seemingly simple problem requires around how many pages now? 15 pages at least, or 16 pages of of derivation. We started at page number 23 and we finished at page number 36. So we required around 14 pages of derivation for such a simple problem, where we could computationally or numerically find it at a much faster, much easier method.
And we haven't even included the convection terms.
Exactly. So yeah, and this is for a simple rectangular flow problem. So I'm just pointing it out that the analytical solution is in fact difficult and tedious in most of the other problems, including this one actually, and therefore we follow CFD techniques to easily find out the exact values.
But the
I hope
advantage, I think, over here is that you have something to check against in
yeah.
a case like this.
Yeah, one thing is we can check again. Second thing is we are not getting a discrete value. We don't have to go and find, we have the continuous value over here,
Right, right.
and this
Yes,
is
you
more
can,
accurate
yeah.
when we solve the
You can
value.
validate the CFD with this. Yeah,
Yes, yes, this would be the ideal way to contain or conclude from the CFD
yeah, yeah,
simulations that
yeah.
we get. I hope this derivation was as interesting to you as it was for me. If you have any doubts, please let me know. Otherwise, we can end the session if you have any other
Yeah,
further
that was
question.
very good. Thank you very much.
Thank you.
Sure, sure.
Good night.
Good night.